start the recording if it's fine. So now this is what we did. Now your question is that we have to find x double dot. My only comment here is, Kevin, that the x double dot for both these fellows, the collar as well as the card, because x double dot means in this direction, the arrow with the pink color. Both these two objects will have the same x double dot, right? Because what we are saying is that as this fellow is going, the rod is connected on this one. I understand your question. Your question is that there is a relative motion. That's your question, right?
Yes, yes.
Hello. Oh, that's your question. If you can. Look. I do understand your point, but even in that case, the answer is correct. The find x double dot for which so we are finding the x double dot for the cart. We have to find the x double dot for the cart because of which, because there is a small m here. Find x double dot for which the collar stays at the location without moving upward or downward. So we have n cosine 60 equal to mx double dot. So the x double dot of the, I think I understand your question. That's a good question. Our hadn't moved. What would have happened to the collar? We do understand that the collar was it would have gone down, right? Because of its own weight. Yes. But since the card is accelerating towards right, that acceleration is responsible for putting this collar upward. Now we have come up with this particular acceleration. If the acceleration is possibly less than 5.7, then this collar will go down because of its own weight. And if this acceleration is greater than 5.7, then this collar will go upward. But the fact that this collar is just hanging stationary right in the middle is because the cart is going in x double dot. That's why now we will not add or subtract anything on this 5.7. This 5.7 meter per second square is the acceleration of the cart towards right, which is responsible for hanging this collar in the center.
Okay, Tawan. So it's just like that means the next acceleration is 0 for that mass.
100% correct. So your initial question, why aren't we adding that to this one? Now you do get my point that yes, essentially you are adding it. Yeah, good. But what you also have to understand, everyone, in fact, when we are starting this topic, I also want you to understand one thing. Everything that you are doing right now, so I'm about to switch the screen, correct? This is understood now, right?
Yes, okay. It's clear, Hujam.
Look, my only comment is that there are two parts of kinematics that you have studied. Oh, we are at 140. Okay, everyone, welcome to another session of dynamics. Look, there are 1 to 2 comments, very critical. I understand that you really want me to grade your exam papers quickly, so you will get the result very quickly. Give me a couple of days, because right during your exams, I think you did observe my throat was very bad. So definitely there was a struggle of health. We have this weekend that is coming. These 2-3 days are dedicated to your exam paper grading. So you will get your results hopefully by next week. No further wait for you. Number 2 comment is, I hope you have watched at least 1 or 2 classes. I did send you a PDF file as well. In case you did not, you don't need to worry. We will continue from here and you can just join us. Number 1 comment I want to make is that we are talking about kinetics now. So we have talked about kinematics. We have seen how to find velocity, how to find acceleration. So there were two parts that we covered. We talked about the point objects, right? And then we started talking about those rigid bodies, rods, collars, connected with a flywheel. It was pretty complicated. Now we are talking about kinetics, right? Kinetics means forces. And this is the first part that we are doing. We are talking about point objects. Now I am explaining this. I did explain in the last class as well. We are talking about point objects. The reason is that I am not giving you the height of this box. I'm not telling you any height or dimensions of this box, although it might seem to you like this, but this is not a rigid body for me. This is more like a point object for me, because the height of the box is of critical importance in general. But since I'm not giving you height, because we are talking about all of this from a point object perspective. So let us do this problem. In case you missed last class, you can all join us. So why don't you all do it and tell me the answer? Find the maximum acceleration that is allowed when applying the brake, before which the box tends to slide or move. So somebody applies the brake. We know this is called acceleration. You can call it deceleration if you want to. So this is acceleration, right? I'm putting on the brake. Now this box can slide forward, right? But I want to find the maximum acceleration that is allowed without this box sliding. So any student who plans to tell us the method, the number one part is you have to draw a free body diagram. Even in an exam setting, if I do not explicitly ask you, you have to make the free body diagram. That's the way it is. So you quickly make a free body diagram without any further ado. So this will be touching the surface. When someone touches the surface, that means you have to draw a normal force. How many agree? Everyone agrees, right? So the normal force is directed perpendicular to this surface. Since this surface looks to me as horizontal, I will make a 90-degree angle right through the center of mass. How many agree? Now, what about the weight of the object? Nice and easy. The weight of the object right through the center of mass is directed downwards. We know that weight is always acting straight downwards. You call this as your mg. We call this as our, how many agree? Normal force. What other forces exist? Coefficient of static friction. So there is definitely friction. So I will draw an arrow and I will call it as friction F. What else? Of course, this whole object is going towards, okay, we have a chat now. Coach, I need to leave 10 minutes before first lecture ends. Oh, okay. I need to go my computer having hard time. Yeah, that's fine. No problem. Just watch the recording. Okay.
Yes. John, can I say something?
Yes.
About the symbols we're using? Can we use F and small r for frictional force and N and small f for normal force?
Yeah, why not? Your question is, can we use capital F, N?
No, N, yes, and small f for normal force, and F and small r for frictional force. It's better that way, so there is no confusion, because N is also Newton. Okay, so instead of normal force, you are telling me that we can use a symbol F? N, the big N and a small f subscript.
This big M?
No, jump N and small f.
N and small f, okay, and then for this one?
Yes, and F and small r.
F and small r, like this?
Yes,
yes, understood. No worries. Yes, you can, of course. Absolutely. As long as you are consistent in your symbols, and it's, yeah, fine. Why not? Absolutely. Why not? Okay. So now what else? This object is accelerating towards right. So I will, without any further ado, will put an arrow towards right that will indicate the acceleration. So you can use entirely different color arrow, because usually on a free body diagram, you don't show the acceleration, right? So you can use a separate color. 1, 2, 3, same colors, this one separate color. As I said, usually we don't put accelerations on the free body diagram. Anything else? Did we miss anything? Sorry? Velocity? No. On a free body diagram, the maximum I can put is an acceleration. Even that is not even recommended. But velocity, I think we will incorporate later. Now, find the maximum acceleration that is allowed when applying the brake. Please understand that 70 km/h will not even show up in your equations. I gave you the 70 km/h because the second part of the question would be, what will be the maximum distance that is required? So 70 km/h will come later. So why don't you tell me the first part? Summation of forces in the x direction is equal to, fill in the blank. Then summation of forces in the y direction is equal to, again fill in the blank. So this part will become mx double dot, and this part will become my double dot. So if this is my box and this is the free body diagram, what is the acceleration in the y direction for this block? Zero, for sure. Yeah, for sure. This block is not flying upward or downward. So for sure, it is zero. So I will get, focus on the left hand side, please. You will always make a coordinate axis y and x like this, nice and easy. My positive is upward, so I will put a capital N like this. Negative is mg, I will put a negative mg. And it is equal to 0. Mg means weight. So capital N equal to mg, that is my one equation. Call it as equation number, let's say 3 or 4, whatever. This is our equation number. Let's call it 2. This is my equation number 1. So from my equation number 1, how many agree? And what happened? Okay, how many agree that I will get the friction force that is nothing more than negative F, because friction is in the left side, plus okay, plus there is no other term in the positive sense, 0, or you can remove the 0, equal to mx double dot. So I'm skipping one step. Instead of friction force, anyone who remembers the formula of friction force in terms of normal force?
N times coefficient of friction.
N times coefficient of friction. Here coefficient of static friction is given to us. So I substituted negative N multiplied by mu s equal to mx double dot. I call this as my equation number 3. So all you have to do is now solve the equation 3 and 4. So N equal to mg, it gives me minus mg, mu s equal to mx double dot. M of the box. So I think it makes sense that you remember that mass is M is the mass of the box. And I get a very beautiful answer of x double dot equal to negative of mu s multiplied by g. Now, what is the value of g? This is System International. It's not 32.2 pound per feet square. It is meter per second square, 9.81. So you substitute minus 0.3 into 9.81. Why don't you all use a calculator? And x double dot comes out to be a beautiful answer of
minus 2.94.
Yes, it seems the correct answer. Thank you to both our students. Minus 2.94 meter per second square. So whoever is driving the car needs to make sure that when he or she puts the foot on the brake, the acceleration, that is deceleration, that is negative acceleration, should not be any higher than negative 2.94. Negative 2, happy. Negative 1.5, happy. Negative 0.5, happy. Negative 2.95, no. The box will slide. And if there is crockery or any delicate utensils might break, right? Now, one of the students did point out the velocity, right? You can see that velocity never showed up till now. Yes. Yes, so that's why negative mg. Oh, no. Oh, I understand your question. That's sorry. Yeah. Oh, no. I think. Oh, so that's a good comment. We have a good question, by the way. Let me answer this. So there are two things. Okay. The first thing is that the maximum deceleration that this can be subjected to is negative 2.94. But your question is that why didn't we substitute negative 9.81? No, we don't substitute. Yeah, I get your point. Like instead of g, why aren't we putting minus 9.81? That's your question, right? Yeah. Why aren't we substituting g with minus 9.81? No, because when we are writing the equations and the arrow is downward, I already took it as minus mg. But I think in the last question in which there was the free drop packet was falling downward in the last class, we did took minus 9.81. Oh, that is a good remark.
Yeah, Hojam, 1 minute. I have, my question is kind of like that because, okay, we have gotten the acceleration to be 2.94. So in which direction? Is it that if the truck is accelerating beyond 2.94, the package will move, or if the truck is decelerating?
I will answer. Yeah. This part is easy to explain. So this part I will explain like this, that if, for example, this car has a deceleration of any more than 2.94, when you put the brake, the acceleration is 2.94, or let's say any more than 2.94, minus 2.95, minus 2.96, then this object will slide forward. If the deceleration is any less than minus 2.94, minus 1.5, minus 1, or even let's say the driver does not even put brake, that is x double dot equal to 0, then this fellow will not slide. Let me answer your questions like this. Please understand this question from another perspective. You can consider it like this. Even if they had asked us what is the acceleration with which this block had gone backward, still you would have got 2.94 as the value, that the moment the person puts his or her foot on the accelerator and the acceleration is any more than 2.94, then this block can slide backward. So I will answer your question like this. Number one thing is that do not substitute negative 9.81 here. I will answer it like this, that when I had put this, I had already taken into account the direction. So that is my answer to your question. When we were talking about that free drop in which there was a packet that was falling on the windshield, I still remember I substituted g equal to negative 9.81. Whenever we talk about acceleration below the datum, I get that. But here I would not prefer to put another negative 9.81 because you can see this green arrow. I already know that mg is acting downward. That's a negative sign that I already have incorporated. So I will not want you to put another negative sign in the g, because I already incorporated in negative mg, right? Are you following me? This is the first part of the question. The second part of the question is, as Ogu mentioned, there is a negative sign here. No problem. Negative or positive, I have an understanding that if this truck accelerates at more than 2.94, then the box can slide backward. If it deaccelerates any in a magnitude more than 2.94 in either direction, the block can slide forward or backward. So my answer is making sense. Because I am the one who told you that the person is applying the brake, right? If I had told you that he or she is putting his or her foot on the accelerator, so what is the threshold of acceleration? If he or she exceeds, then the box will go backward. You would have done exactly what I have done, right? So it's just the interpretation of result. X double dot equal to negative 2.94, no problem. We do understand the meaning. Now the last part, both the questions were exceptionally good, by the way. Why didn't we put negative value here? Well, we already have taken into account the direction. I don't want to put another negative 9.81. That's the first remark. Second is, it's just the interpretation of the results. So if I now ask you, what is the distance that the truck will cover before it comes to a stop? That is the minimum distance that it requires to stop the truck. So it's a constant acceleration problem. They told me the formula for constant acceleration, and all I have to do is make a substitution of negative 2.94 is equal to Vf square minus 70. Now you have to be a little careful here. It's 70 kilometer per hour. So multiply with 1000 for meter and divide with 3600 for second. I'm using SEC to differentiate from delta S. So I get a very beautiful answer for Vf. And I will be waiting for our students to tell me. Oh, not VF, sorry. Sorry. Thanks for mistake. VF is 0 because the truck comes to a dead stop. So it will be VF square minus VI square, sorry, delta S.
You get 4.41 meters.
64.4.
4.41.
No, it is, I think there is a square that I forgot. So it's my mistake. Now you have to do it again.
$19.4.
Really? I still don't have the, so delta is, I have as 64.4. No. So Kevin will double check. Yes, no. Umut got the answer. 64, okay. As long as you are getting somewhere around 64, it's fine. All said and done. Should we continue? So let me see if our online students have any questions. Gail, Kevin, Mehmet, Mohammed Khatabi, Rivis, Haman, Ugu. No, yes. Okay, now one thing that you have to understand, I keep on saying the same thing. This is not a rigid body problem. Otherwise, I would have to give you height of this object as well. Because just imagine if somebody applies the brake, there is also a possibility of this whole box to topple, right? This box can flip. Just imagine if I change the dimension and give you an object like this. Is it the same problem as before? No, because this is more susceptible to topple. But where did the height go? Because I never gave you the height, because we are considering it to be a point object. We are not talking about rigid body kinetics yet. And another thing is, in free body diagram, just 3 arrows are sufficient. The X double dot you can put with an entirely different color. Okay. Great. So, okay, on that note, what we can do is we can talk about one more comment. When it comes to the kinetics, that is talking about the forces, there are technically 3 ways in which you can handle a problem. The number one is the summation of forces is equal to mass multiplied by acceleration. That's your Newton's law. So we have done, I think, 4 problems till now, 3 or 4 problems. 3 problems, I believe, from last class, 3 or 4, and 1 problem right now. In all of the problems, you had the same question. You had to find, I don't know, some acceleration, some velocity, whatever. But it was rigid kinetics problem, right? You had forces, you had to deal with them. What you can do is you can also solve problems by 2 more methods. One is work energy and one is impulse momentum. Now, all these 3 fall under the same category of kinetics. Now, there are some problems in which you can still apply the summation of forces equal to mass multiplied by acceleration. It will again give you the unknowns, let's say velocity or whatever, but it will be very complicated. So what you do is you either go for the strategy 2 or you either go to the strategy 3. All these 3 will help you in finding the force, acceleration, or whatever. Second thing is, we are still talking about point object. We are still not talking about rigid body till now. So for work energy, that is our method 2. I will come up with few comments. Number 1 is that if we are applying work, then by definition, it is nothing more than, so U stands for work, number 1. It is work applied on an object is nothing more than the integral of F and ds with the dot product between them. Force is a vector, ds is the change in the position, it's also a vector, this is a dot product. Now, what they have always told us is that if you see the complete chunk, the integral FDS, I'm talking about this chunk, please focus here. This is nothing more than the area under the Fs curve. So for example, if this was the mass and you are applying a force in this direction, right? We know that this object tends to slide in the right side, right? Now, if I define my ds from this reference line, then all you have to do is write the formula integral FDS. Just imagine that someone tells me that the applied force is 50 Newton. 50 Newton in the x direction. 50 Newton in the x direction. So for example, there was some component, there was some original force. Theta was given to me. So I will do a cosine theta. And final answer for Fs is 50 Newton in the x direction. All you have to do is, for this constant force problem, your work is nothing more than this 50 multiplied by the change in the distance. So I believe you also went over this from your physics classes as well. I believe. So you can see that this blue arrow doesn't contribute. What contributes is this blue arrow, right? So let's say if this was, let's say 100 Newton, and let's say this angle was 60, then 100 cosine 60, let's say, is the 50 Newton, and this 50 will appear here. So force in the direction of the displacement. Now area under the curve means that, let's say this was the path that the object followed, right? Then the work is nothing more than the area under the curve. So this whole chunk will be your work. Similarly, let's say if in another scenario, object goes from this location 1 to location 2, right? And the applied force was varying like this orange line during the path. Then the area under the curve this time is this chunk. This will be your applied work. That is work. Okay. And of course, you're talking about this F. So it is the force in the direction of the distance. You can, yeah. No, I think this is coming from integral FDS. So we just substitute just simple F here. Okay, now anything else? Okay, one more comment here. Let's see if any student wants to help. What about work by friction? So it will be because of the friction force multiplied by delta S, where negative sign means that it is opposing. So the units of our work is Newton meter, which is equal to nothing more than joule. And let's talk about one more thing, that this U12, let's say we can say that this is equal to the work that we are applying on an object is equal to the change in kinetic energy for that object plus change in potential energy for that object plus, let's use another thing, change in elastic potential energy. So any applied work gets converted into these three components. This is given as Newton meter, that is joule. Same story goes for this fellow. Same story goes for this fellow. Same story goes for this fellow. Correct? Everything is clear till now, right? So it's just more like a revision from our physics classes till now. Okay, now what I will do is I will write here one more time is equal to delta T plus delta VG plus delta VE. Now, what about delta T? Let's see if anyone can help us quickly. What is the change in kinetic energy? So let's say we are talking about from point 1 to point 2. Half m multiplied by V2 square minus V1 square. So the units are kilogram meter per second. So it will be meter square per second square. So these units are nothing more than, again, joules or Newton meter. Let's talk about change in the gravitational potential energy very quickly. It will be equal to change in gravitational potential energy. How many agree? Nothing more than delta Vg equal to, let's see if anyone can tell us, mg delta H, right? Now delta H, please remember, is parallel to G. So let's say we have an object like this at location 1, you take it to location 2. We can't care less whether it is going horizontal. We are more concerned about this location, this change. That's your H. That's why I said it is parallel to G, because your G is also in this direction. So you're going from 1 to 2. Parallel or anti-parallel, it's the same thing. Now, what about the last component? Let's go at sonic speeds. Let's say this is a spring that I'm creating. You can all help me with this one. This is a spring, and this length is L naught. Its original length, that is rest length. Let's say we stretch it to, from here, we stretch it to this is the L. Then there is another case. This is the new length again. Again, this is L. So this was rest length. This is the new length, that is L. And in this case, this is the new length. In one case, you have extended. In another case, you have compressed or shrunk. So delta L will be the final length minus the rest length. And now we will request one of our students to tell us the formula. What will be the elastic potential energy? So you applied work, it can convert into 3 components: the change in the kinetic energy, the change in the gravitational potential energy, and the change in the elastic potential energy. So it can convert into all 3 components. Or if only 2 fellows are present at a time, then only 2 fellows. If only 1 fellow is present at a time, then only 1 fellow. But in maximum, we will be considering these 3 conversions. So anyone quickly? Anyone remembers?
Half K E square.
Half K
E square.
Yes, half K half K X square. I remember from my student days. You are right. I will be using it in a more complicated way. Half K delta 2 square minus delta 1 square. It's actually the same thing, half K X square, where X is the change in the displacement. I'm just using it as delta 2 square minus delta 1 square. Yeah, because for example, if this was the original spring and at location at state 1, let's say someone had extended the spring like this, and at state 2, the spring had been expanded like this. Then first I will find delta 1, which will be L minus L naught. Then I will find delta 2. Again, this is my new L, and this is my old L, and this is my L naught. Then delta 2 I will find as again L minus L naught. This is my new L. Then finally delta VE is equal to 1 over 2 K into delta 2 square minus delta 1 square. So I present it in a more complicated way, or in a more generalized way. Another thing is that the applied work can be stored in the spring. Either you stretch it, either you compress it. Either way, there would be elastic potential energy, right? Agreed? So either you stretch it, either you compress it. You compress it, there is elastic potential energy and it wants to expand. You stretch it, it wants to contract. Either way, you will have elastic potential energy that will be stored because of the applied work, So I apply work, gets converted into change in kinetic energy, can also get converted into change in gravitational potential energy, can also convert into change in elastic potential energy. All three of them, either one of them, or a combination of two. Let's say if there are more than one point masses in the system or more than one mass in the system, then you will put summation signs all over the place. More than one spring, more than one masses, right? You apply a work on the system that has 2-3 masses, their velocities change, their gravitational potential energies change. There are 2-3 springs sitting. Okay. Anything else? 6, 5, 4, 3, 2, 1. So let me add few comments then.
1 minute, William.
Yes.
Can you go back to the previous slide? Can we substitute F times D for T?
Can we substitute integral FDS where?
For changing T?
No, here?
Yes.
No, but the way we are looking here is like this. The applied work is integral FDS. It gets converted into this component plus this component plus this component. So
Okay.
you can think it like this. I had a ball, I apply a force, right? It covers a distance. That's my applied work. So initially ball had a certain velocity, then the ball's velocity changed. So this is the change in kinetic energy. I had a ball, I throw it up. There is a change in potential energy that happens because of the applied work. I had a spring, I pull it because of my applied work. There is a change in elastic potential energy that happened. So I completely get your point when you say, can we substitute this here? But no, don't do that. This is your left-hand side and it is equal to the 3 components. Okay. I think it's quite a while after before that we went to theory and all of that. So today is one of those days. 6, 5, 4, 3, 2, 1. A few comments that I will write. Number 1 is your delta T is positive. Delta V is positive if speed increases. And vice versa, etc., whatever. Then please remember that the change in kinetic energy is a point function. And one of the students will explain us the meaning of point function. I will also explain after a while. Another comment is that your change in gravitational potential energy is positive if the height increases. And vice versa or etc., whatever. Similarly, it's a point function. Again, some of the students will explain what is the meaning of point function. Then what about our elastic potential energy? Anyone who can tell us? I cannot say whether it's positive when the spring, like I cannot talk about positive or negative for a spring, because if you have a spring, you pull it, elastic potential energy increases. If it's sitting like this and you shrink it, elastic potential energy increases. If it's stretched like this and you do a little bit of like this, elastic potential energy decreases. But beyond equilibrium, if you compress it, elastic potential energy again increases. You do understand this, right? So similarly, if it's completely compressed, I pull it a little bit, its elastic potential energy decreases. But when it is at equilibrium and I stretch it more, its elastic potential energy increases now. So for delta VE, I cannot say positive or negative in English form like this. All I will say is it's a point function. That's it. I will not add any more things. And I can say, okay. Now, I will also add here.
Jojo,
Yes.
maybe you can say that it's always positive because of the change in length square. Whether the change in length is negative or positive, as long as it's square, it's always going to end up becoming positive.
No, but you have to understand is that what my point is that there is a delta 2 square minus delta 1 square, right? So for example, just imagine that if I have a spring that is, let's say, stretched, right? A lot of elastic potential energy. I leave it a little bit. Now is elastic potential energy more or less? Now it is less. If I put it a little more, elastic energy is less. If I bring it to equilibrium position and leave it, its elastic potential energy is 0. If I compress it, its elastic potential energy is more. So it depends on your delta 2 and delta 1, Kevin. So elastic potential energy can decrease or increase. So stretched. Now I put it a little like this. It's less stretched, elastic potential energy has decreased. Now work is not a point function. It is a path function. It is a path function. It is a path function. So I have an object that is, let's say, on this floor, that is friction. I bring it from here to here, right? So it's right. And let's say I take it to that side and I 10 meters there, 10 meters there, and then I bring it here. Of course, I will have to do more work because work is a path function. It's not a point function. So a point function only depends on starting on the, let's say, starting and finish, state 1 and state 2, or point 1 and point 2, state 2, irrespective of the path followed. Whereas path function depends on path or dependent on path followed. That's why I said kinetic energy is a point function. I honestly don't care how we go from 1 to 2, but as long as this ball is at 2 meters per second, this ball is at 9 meters per second, that's my 1, that's my 2, and I'm happy. I can't care how did I take the ball from here, let's say, all the way up to this location. I could have taken it right, left, don't care, as long as the ball goes from here to there or there to some lower height. That's my 1 and 2. That's my gravitational potential energy. Similarly, elastic potential energy is point function. I can't care less. Spring was here and then spring became like this. All I care about is the point 1 and 2. Okay, that brings us to our first problem. Do we need a break? Yeah, it's just a lot of theory. So we can have a 5-minute break. 2:31 sharp, I will start, and our online students can ask me questions or the in-class students. Yes, yes. Yes.
Victor,
Yes.
you remember, yes.
Yes, you asked me before as well.
In this question, first one, totally, I don't remember what.
There was also normal acceleration
Like
that you had to find. Yeah.
we find V
Hmm.
and we find A.
Hmm.
And acceleration has,
Tangential acceleration is 0, but normal acceleration would be there.
yes, the two components, right?
Yes. So
A.
tangential acceleration
Right.
for no slip condition was 0.
Yes, D
But
component and D
yes.
component.
But normal acceleration,
And two components, I and G component.
that's what I'm saying. But normal acceleration
Mhm.
was non-zero.
Okay, yeah.
Tangential was 0. I still remember you were asking me this in the
Yes,
exam
yes,
hall,
yes.
but I did not answer it
Yes,
because
yes.
it was an exam.
Okay, okay.
But you do understand that normal acceleration would be non-zero.
I just like it, hocam.
Good.
Two components.
Hopefully, you will.
Yes, hocam.
Everything
Did you
will.
read?
Huh?
Did you start to read?
Yes, I have started,
Okay.
but I will finish on weekend. So it is very close to, I will say here. So it's just bad drawing. You can start right from here probably. It's negligible here. So this is what we are interested in, because the question says that we have to find if the F is 140 kilonewton and the mass of the object is 24 megagram. So I think everything is given right. Now we can start the question. So we have to find the V2. Okay. Okay, welcome back everyone. This is our question. The question is that on an aircraft carrier, we have this aircraft, and you know that there is this mechanism on an aircraft carrier where the aircraft is thrust using some sort of catapult mechanism, and in this way, on a very short runway, the aircraft can take off. So 140 kilonewton is provided by the thrust of the aircraft itself, whereas the catapult mechanism is generating this load P. Now the load P by the catapult is on the y-axis. The distance from 0 to 90 meter is presented here, and you can see that the catapult is giving this enormous force, like right from 0 meter to I don't know 4 or 3 meter. You can see the force has skyrocketed, and then you can see that the force given by the catapult decreases like this. The question is find the V2 as the aircraft leaves the aircraft carrier. So I hope this question is clear that this is the catapult force. This 140 kilonewton is a constant force by the aircraft's engine. In order to do this question, the first thing you will do is U12 is equal to delta T plus delta Vg plus delta Ve. Now, what is the change in the gravitational potential energy? Anyone? Change in the gravitational potential energy is, there is no change in the height, so 0. Okay, now I told you catapult. Nobody is telling us that the catapult is a elastic rubber, right? So that would be just a stretch of imagination if you think it like this. So there is no spring, there is no rubber band, so elastic potential energy is also 0. Now U12 although will have two components, one component of U12 will be by the thrust of the engine, and the second component will be using the catapult force. So U12 is equal to UF plus UP. Sorry? Thrust of the aircraft. So it's an aircraft sitting on a carrier. We know that when aircraft is sitting on an aircraft carrier, there is very small distance during which the aircraft has to take off, right? And there is this catapult mechanism on an aircraft carrier that gives this catapult force to the aircraft so that it can fly. This 140 kilonewton is by the thrust of the aircraft itself, the force of the engine, and the rest catapult force is given as P. So if it's confusing, I can divide it like this using a red arrow. That is the force of the engine, and orange P is the force of the catapult. So now just finish the question. UF is nothing more than F delta S, and UP is nothing more than area under the curve. So just imagine if you had started to use Newton's law, it would have been very complicated for you. Area under curve. So here I will stop and all of you will do the question yourself. Now you have to assume a triangle, by the way. Students who are getting confused about this little distance, probably on your notes, you can just barely join this here. Even if you don't join, it's just, of course you will join it somewhere. So probably you can join it a little bit here, or probably I can just use a big pointer like this. Something like this.
Is it 24 mg or 24 milligram?
Megagram. Capital M will stand for mega. Okay, so why don't you all now give me the answers for this one? So what is F delta S? It will be 140 kilonewton because it's a constant thrust, multiplied by delta S is 90 meter, 90 minus 0, 90 meter, plus area under the curve. Consider this to be a triangle. So students who are getting really confused, I will put it like this. I'm making a beautiful rectangle, and I'm on the y-axis, I'm plotting F, and on the x-axis, I am making S. So this beautiful rectangle is the 140 multiplied by 90. And then I will make a beautiful triangle here. Although I'm sure everyone does not agree, this does not look to me as a triangle, but we have to consider this as a triangle. I mean triangle plus rectangle. Or probably making a diagram right now is complicated. You already have this. So it will be 1/2 into base 90 minus 0 into height, which is 1100 minus 65. This is not 1100, by the way. I think it is 1035, and it's my mistake. So please make this correction. Students who are planning to continue with 1100, they are also fine. No, sorry. Wait a second. It is 1100. I apologize. So it will be 1/2 base into height. So height is 1100 minus 65. Yeah, my bad. 1100 minus 65 into kilonewton, and this is your meter. Plus, you have to add one more component, that is this rectangle. So it will be 90 minus 0 multiplied by 65 minus 0. I think we are making our life complicated by subtracting these zeros. So U12 is equal to, this is 140 into 90. So I will just wait for students to tell me the answer.
Excuse me, Hajam. Why did we add the last one?
Yeah, yes, I will explain this. 65 megajoules.
65,021.
So it will be, it's in kilos, right? Everything is in kilos. Yeah, so it's 140 kilo and multiply by 90 plus this 1100 minus 65 kilo, and there is this meter and kilo, right? So my final answer will be actually in 65 into 10 power 6. Yes, Kevin. So we are adding because at the end of the day, it's area under the curve. And if you see, if I talk about area under the curve, this portion will also be included. Are you following me? Because it's area under the curve. That's what the rule says. So although it might look to you, because at the end of the day, this does not jump from here to here, right? So of course it's a continuous line, because if the catapult load is 0, it does increase, but in a finite distance. So if it is confusing all the class, so I will just add one change. Probably if anyone is getting confused, you can just connect it like this, no? But still it's area under the curve. That's the rule. Because I can also argue that within few even meters, let's say, or half a meter, it jumps to huge values. So it's impossible for me to present here, probably a vertical line. Okay, 65 megajoules, right? Because of the 10 power 3 that was already sitting here. Agreed? Okay, why don't you give me now the change in kinetic energy? I mean the final velocity, if the V1 of the aircraft is 0. So let me write it here. 65 into 10 power 6 is equal to half. Now be careful. Convert the mass from grams to kilograms. So it will be 24 into 10 power 6 is grams, 3 is kilograms, into V2 square minus 0 square. So V2 comes out to be
For John, 1 minute. You say mg is what?
megagrams. It's capital MG is megagrams. Yeah, I know it's confusing, right? Because this is probably the first time even in dynamics when I have seen somebody give the mass of an aircraft in megagrams.
I got 73.6.
You know, 73.6 seems correct to me. I agree with you. Is this clear? Ogo, Kevin? Yes, no, no. So just so that students don't get confused, it's something like this. It's one continuous line. Is this question clear? Is this clear why? Sorry? Mega is 10 power 6, and I had to divide it with a 10 power 3 because I am not allowed to use grams in my equations. Kilogram is the standard system international unit. So half mv square, your mass should be in kilograms. not grams. So what I did is instead of using 24 into 10 power 3, 24 into 10 power 6, I divided by 10 power 3 to convert it into kilo, and I used 24 into 10 power 3 kilograms. Meter per second square. So is this clear that the applied work is in the form of the thrust of the engine plus the catapult that is providing the force gets converted into the change in kinetic energy, and the change in elastic potential energy or change in the gravitational potential energy is 0. So I'm stopping here for 2 minutes, 2:49. You can just think about it, ask me any questions. Okay, let me just add one comment. What we have been doing from the beginning of the semester till the rigid body kinematics, we have been using that formula, the ginormous V formula and acceleration formula, to find the velocity and accelerations, right? So you might be thinking, what on earth were we doing? What was the point of it? So consider it like this. In the exam, do you remember I asked you to find the acceleration of that wheel, right? That was a rigid body problem, right? So the wheel was going, I asked you, tell me the acceleration at the center point. I still remember. So let me put it like this, even right now. What was the force that was acting on that wheel at the center? Mass multiplied by acceleration. You did find the acceleration at the center. You multiply with the mass, you get the force that is needed for that wheel to go at that acceleration, or vice versa, what force it will impart if I was standing in the path of that wheel. My point is, you have already done the hard part. You knew how to find the velocities and acceleration, and you can just use summation of forces equal to mass multiplied by acceleration. So kinematics, you get velocities and accelerations. Kinetics, you use summation of forces to now find the forces. Is it clear to our online students? Yes, no? Okay, everyone. I believe everything is clear. So this is your class problem, by the way. Why don't you all do it yourself? You know, if there was no online component to this class, I would have given you this class quiz, let's say. But since it's online plus in class, and but still you will do it. There is a spring. Even this can be considered as a spring, but I think instead of using this, I'm using this. Now, there is this ginormous, something like this structure. The structure has a collar. So consider it like this. Give me 1 minute, please. I have to make sure that the diagram is clear. So something like this, a rod. On this rod, there is a nice collar like this that is sliding. And this collar is 50 kilograms. Now it is connected like this to this spring. The length of this spring is 1 meter. That means the rest length, the equilibrium length, the unstretched length, the uncompressed length. And what happens is that this distance is 1.233 meters. I'm not sure the logic behind giving some length up to 3 decimal places, but I will not argue and I will just write it. Okay, now this distance is 1.2 meter. Now what happens is that there is this string or rope that is attached to it like this. And of course, probably it little bit bends, but it's okay. It's a rope or a string. And now it goes like this. What happened? Yes. This is our, oh, load P is acting like this. Now the load is 300 Newton. This distance is 0.9 meter. Let me go from here to here. You need to ask me questions if the system is not clear, because if the system is not clear, then you will not be able to solve it, by the way. And the system is a little complicated, I understand. This is a rod, and the rod, let's say, finishes like here. And I will use very quickly color as well. How many agree? Here comes the question that you have to answer, everyone. If the spring is 80 Newton per meter, and this distance is 1.2 meter, which is wrong. It is going all the way up to here. Please give me 1 second. It is going all the way here. Something like this. Yes. So find what we have to find. Find VB. If this is your B and this is our location A, problem is really complicated. Then we have to find VB. Yes.
Is there an angle between the mass and the rope?
Okay, actually there are two students who are asking the question. If you can give me 1 second. Your question is, sorry.
It says that string is 1 meter, but it also says that 1.2.
Oh, yeah, got it. Okay, I will answer this. The answer to your question is that the rest length is 1 meter, but the collar is already in a stretched position. So hence, in the initial state, it is 1.233 meter. Right? You do get the point. Okay. And Kevin's question is?
Is there an angle between the rope and the mass?
Is there an angle between the rope and the mass? So this is the rope that is connected to the mass, and we can certainly find the angle. I did not understand your question, by the way. If yes, so for example, between the rope and the mass, like this angle, yeah, of course, there is an angle, for sure. Sorry, and what is that angle? So it's 1.2 meter here and 0.9 meter here. That's all the information given. And just to be clear here, if you are a little confused about this line, just consider that this is more like a triangle kind of a formation. It's barely a triangle kind of a formation, but no further information is given. The rod like this one? No, the green one. Huh? Oh, okay, yeah, okay, got it. Let me explain to this. Yeah, okay, yeah. Let me explain the system. Everyone, the collar is sliding on the green rod. So what happens is that this is the collar all it can do is it can slide along the rod. That's all it can do. So as the rope is pulling, the collar can go to the right. The spring will resist its motion. And this blue line is giving us the rope. And I will again draw it because I'm scared that everyone is just getting confused by this rope. So I'm putting an end to the confusion. The rope is like this. And no further angle is given. We have to find all the angles ourselves. The question is that if the object starts from rest as VA equal to, let's say, 0, find the VB. So let me ask Kevin, is the question clear? Because you had a question, right?
Yeah, I get it. Because I thought that since is a spring, it can move in the one direction. So,
No, something has happened to your voice.
like Justin helped clarify, because he asked the questions I wanted to ask. Because I thought that it's a spring and the road, so the road is free to move in the Y direction.
No. The rod is fixed. The spring is holding onto the collar. As I'm applying the load from the top, the collar wants to slide on the green rod. The spring is trying to pull the collar to the left. That's the system. And this is 1.233 meter. On that note, the first thing you have to do is write the equation. If you call this as, let's say, location 1 and this as your location 2 or A or B, whatever, U12 is equal to the applied load is applied work is nothing more than equal to the change in kinetic energy that gets produced, the change in gravitational potential energy that gets produced, and it is also being utilized into overcoming, it is also utilized into increasing, decreasing, whatever, the change in elastic potential energy. Now, all you have to do is first handle this one. What is the change in the gravitational potential energy? 0, right? Because even if you say that the rope is going up, the rope is massless. The collar is sliding towards right. That's all. Anything else? What about the applied load? So it will be U12 is equal to, the applied load is constant. So it is F multiplied by delta S. So which is equal to 300 multiplied by delta S. So what is the delta S? When the collar goes right till the extreme, it will be 300 multiplied by. So you need to understand that the load is acting at an angle, right? So it's not straightforward. In order for you to find delta S, you need to know that it will be nothing more than 1.2 square plus 0.9 square. That will be the hypotenuse minus minus 0.9 meter.
But yeah, I just saw for the angle and I got 36.9 degrees.
So you got the angle?
Yes.
Okay, so why don't you do one thing? If you have got the angle, then proceed by using the component and let's see if our answers match. So what I have done is, I think your method is easier than this method, by the way. So what I have done is, it's 1.2 square plus 0.9 square root. it gave me the hypotenuse, and I subtracted because you need to understand that this collar will sit here, right? From here, it has to come here. So when the collar is sitting here, it has this amount of, let's say, rope or whatever. I subtract the 0.9 meter, it will actually give me the delta S, because if this load is acting from here, the load will, let's say the rope point is here, it will go, let's say here. So this distance is delta S that I have calculated. So why don't you all proceed with the 36.9 degree, whatever. If it's not clear, let me put this way. This was the length of the rope, right? So look, now the rope will be here. The collar comes here, right? Everyone, please focus. Where would be the rope? The rope would be like this, right? Please tell me whether you agree or not. Look. Okay, then the collar arrives here. Right here. Please focus here. This part is important. Look, where is the rope? Okay, not the best way, I think. I can put the collar a little towards the left. It's okay, but you do get the point, right? So let me put it like this. So approximately, let's say it is somewhat like this, approximately. So what I am saying is, I subtracted this distance, that is around 0.9 meter, with a little bit of error, of course, from this distance. So let's say this is my S1 and this is my S2. Or yeah, S1 minus S2 or S2 minus S1, whatever. Or you can call this as SA. And you can call this as your SB. And this gives me delta S, SA minus SB, because this is how much the rope from here has gone here. This is how much rope has gone to right. Let me use a yellow marker. Is this clear or it has become more confusing? No? Yes? What about that 36.9 degree? Why don't you proceed with the 36.9 degree and tell me what do you get?
No, Hojam, because if I use the angles, and if you use the angle, I don't think it's correct. The one you're doing makes more sense.
Really? Because honestly, I got impressed by that 36.9 degree. I myself kind of dislike this way because it takes too much thinking. That 36.9 degree kind of gave me hope that
as long as you're pulling the rope, the angle is changing.
yes, excellent answer. Yes, you are right, because at every point the angle changes. So you are 100% right. Yes, it's not it will be impossible doing that way. So apparently this is the only way. Now that you have found U1, 2, let me use, let's say, this color. Yes, Ogu. If the angle keeps on changing. Look, the point is that at every point, if the angle keeps on changing, but what I am interested is the U1, 2, right? Now it is a path function, I do understand. But what we are considering is that this is a frictionless fellow. So all I'm doing is U1, 2. I am going from here to here. So my concern is only one: force multiplied by delta S. Force is constant. Integral F delta is my concern, right? integral f delta s. What is f? Fortunately for me, it is constant. It will pull out of the integral, so you are left with f integral delta s. The delta s is the change in the distance, the change, and it is nothing more than this distance minus this distance will give me how much the rope has proceeded from here to here, which is this minus 0.9 meter. It is a little confusing, but that's the only possible explanation. Now, all you have to do is, why don't you all help me with the last part? That is delta t, which is half m v2 square minus v1 square. And why don't you all also help me with the change in elastic potential energy, which is why elastic potential energy? Because the applied load is being utilized in not only accelerating the collar, but it is also being utilized in overcoming the spring, over the elastic potential energy of the spring, the resistance of the force of the spring. So it will be 1/2 k multiplied by delta 2 square minus delta 1 square. So if you dislike this a and b, why don't you put a 1 and a 2 here?
For the work done by spring, you get 79.97
I will
joules.
have to double check. I think you are right, but yes, 80. Very good. 100% correct. But I have to go to the next slide because it's just getting complicated here. So everyone, can you please give me 1 second? So I will write U12 is equal to half multiplied by, what was the mass, by the way? It was 50, I think. Then it was V2 square or VB square, whatever, minus V1 square, which is equal to 25 into V2 square minus 0 square, because I think V1 was given to me as 0. So it gives me 25 V2 square. And as Kevin told us, what am I doing? I mean delta T, everyone. Sorry for that. Then delta VE, as Kevin told us, 1/2 K into delta 2 square minus delta 1 square, which is equal to half. What was K? 80 Newton per meter into delta 2. So I think we have to be now careful. It is delta 1 is 1.233 minus 1. 1.233 minus 1, which will be 0.233. And delta 2 is the distance that we all calculated together, which was this huge chunk, the delta S. And I had to subtract the L naught and I will get 1.433. And finally, I get a beautiful answer of 80. It's funny that it was 80 Newton per meter and I'm again getting 80. And now substituting U12 is equal to, let me use different color. It is equal to P delta S. I get an answer of 180 from the previous slide.
Yes, Tamam, that's correct.
Yes, and which is equal to 25 V2 square plus 80. And I get V2 as okay, I think
2 meter per second.
2 or 12.
still, you get 25 divided by 100 is 4.
Okay.
Then square root of 4 is 2.
You're also getting 2?
Yes.
2.6. So we have two answers, 2 and 2.6. I think both of them are fine. Let me write the answer. Okay, one of the students can double check, but I can talk about one more thing. What about this 1.433? So can anyone tell us what is the delta S that you got? Probably that will help the students.
Huh?
Delta S.
For where?
0.6. Okay, 0.6. Okay. It is 2?
Yes.
Okay, so Kevin is right.
Yes, Sojam. So if you use angles to solve it, you get 2.88.
Okay.
So it's not correct.
Okay. And one more thing, this delta 2 that we got 1.433. How can anyone double check? Delta 2 is from 1 point. Okay, so we subtracted 1.233 and 0.6. How did we get 1.433? Just double check this one. This is L2 minus L naught. This is L1 minus L naught.
The 1.433 is 2.433 minus 1.
Okay, and 2.433 minus 1. Excellent remark. You are right. And this one is L1 minus L naught. So it is 1.233 minus 1. Good, good. Thank you, Kevin. He's right, actually. And if it helps you in any way, you can just consider this collar to be a little smaller in width, so you do not get confused. Why aren't you taking the length of this one? So you can, on your notes, you can put a collar like this big, so at least you don't get confused. Should I go to the previous slide and show you the diagram? Is it clear? I think it was a tricky problem, right? We have a chat message. No. Okay. Okay, we are stopping here for 1 minute. Just tell me if it's not clear. Okay, Jen, I think no one is asking any questions. 654321. So why don't we talk about few things? I think I will stop at 325 or 322. Just give me 1 second. I will just talk about briefly The third piece of the puzzle, that is impulse momentum. Very briefly, and you will also get your homework assignment in the next one day. It will cover two portions, the pulleys and this part. So I will write this formula. Summation of forces is equal to mass into acceleration. How many studied fluid mechanics? Everyone? No one? Oh, no.
I think what I think.
Okay. Well, there was one formula that they used to teach us in fluid mechanics that I always really like. That was m dot into v2 minus v1. But anyways, it's immaterial because I just thought about mentioning that one. But if many students did not take fluid mechanics, that's fine. Now it is equal to d by dt mass velocity. How many agree? Everyone agrees, right? So what I did is acceleration is dv by dt. I pulled out the derivative. So how many agree that I can write it as rate of change of linear momentum is force, right? Let me demonstrate it. Break, by the way. Let me use a pen. So you see, this is a pen. So you will see the rate of change of momentum will be force. Like there it goes. So rate of change of momentum is the force, right? There is a change of momentum that happened for that ballpoint. That is force. Okay, so what we can do is we can define linear momentum that is g equal to mass multiplied by velocity. How many students of our class agree that if the summation of forces is equal to 0? Okay, anyone wants to comment? Then this means that d over dt of g equal to, and that means g equal to constant, right? Because the time derivative is 0 of the g. So how many students are saying right now, why don't you write summation of forces equal to g dot, everyone remembers the dot, right? D over dt operator can be represented as a dot. It is equal to dg by dt. So I will use a different color here, integral t1 to t2 summation of forces dt is equal to integral g1 to g2 dg with a vector. So usually I remove these arrows when I'm talking about integrations because that's fine. So how many students agree that delta G becomes equal to change of area under FT curve, right? Area under FT curve. If you don't want to put summation, that's fine. But I think summation is good. Area under the FT curve or FT graph. So previously, you need to give me 1 second, please. When we were talking about the area under the FS curve, I think area under FS curve, which methodology was good? The work energy methodology was good. When you're talking about the force time, whenever your problems have time involved in it, force time curve, force is a function of time, time is given, force you have to find in function of time, then you want to go for this third strategy, that is the rate of change of linear momentum. Are you following me? Force in any case is generally a function of time, right? But if someone explicitly gives me force as a function of position, you follow the work energy methodology. But if someone gives me explicitly force as a function of time, there is no point in going for the work energy principle, although you can keep arguing that force is still a function of position. But if someone explicitly gives me force as a function of time, I should follow the strategy number 3. So delta G will give me area under the FT graph, and boom, the question will be over. So can anyone tell me what is the meaning of this portion? Let me use red color. You need to tell me what is the meaning of this. Have you heard about this chunk before? And what about this chunk? So this is impulse, and this fellow is momentum. This is your impulse momentum relation, that the impulse is equal to momentum, or you can also say that rate of change of linear momentum is equal to the applied force. I usually like this expression, but rate of change of linear momentum is the applied force, or is the force. But you can also say that impulse is equal to momentum. I already demonstrated by throwing that pen, so it's clear. I am giving you a take-home task. So 7, 6, 5, 4, 3, 2, 1. And then I will call it a day, because we don't have time, by the way, right now. So this take-home task I will do in the next class. I'm not leaving it, but you do it yourself and then tell me whether you were able to do it or not. So someone gave me this curve, and they said that the force, applied force, is a function of, explicitly a function of time given to me like this. So I immediately was like, you know what, I'm not going for work energy principle. And they also told me that the behavior is like this. And I was like, okay, what is the behavior? They said the behavior is like this. They also told me that this dynamical system is actually a mass. Someone is applying load on it. Mass is 10 kilograms. And it is moving on this surface. They also told me that the surface is frictionless. They also told me that this is 100 Newton. They also told me that this is 20 Newton. They also told me that this is 0 seconds. They also told me this is 15 seconds. They also said this is 10 seconds. And this is somewhere 5 seconds. I don't know. Now the question says, find V2 after 10 seconds, V2 after 15 seconds, if the object was stationary at the beginning, at, of course, t equal to 0 second. So if V1 is equal to 0 at t equal to the second, why don't you all find V2 after 10, after means at 10 seconds, at 15 seconds. So I don't want to exceed the time. 3:26 it is on my laptop. Is the question clear? Yes or no? Okay, thank you everyone. Bye bye. Have a nice day. See you. Bye bye.
See that there?